Great. So it's a great pleasure to have Corey Jones. He'll talk about the SymTFT on the lattice. So please take it away.
Okay, yeah, I feel a little bit what's the word? Not precocious. I'm giving a talk called SymTFT on the Lattice to this group is a little bit preaching to the choir. I'm not sure. I'm looking for some idiom to describe how I feel. But anyways, I'm going to do it anyways because my perspective is a little bit different. So I'm going to be talking about SymTFT on the Lattice. I'm working in 1+1D, as many of your all's papers have been. But the main difference with this perspective is that we're working in infinite volume. Okay. Um, and the main reason why that I want to work in infinite volume is because that's the place where you can really formalize SymTFT as like an abstract model independent structure. And then you can try to prove classification type theorems. So for example, like you guys know all about like doing SymTFT stuff on the lattice, but in all those examples, you start with a fusion category and a module category and you build a Hilbert space and you build a Hamiltonian from the operators and you apply your the categorical Landau paradigm. You do all this stuff, but you know kind of what the answer is and you use it as input. But if I just kind of handed you abstract like Hilbert space with operators and said find the SymTFT decomposition and find the states that are Lagrangian algebras, it's like not even clear what that means, right? If you don't have the input from the start, like what do you mean by SymTFT decomposition? And so if you can give an abstract definition of this sort of thing, you can start trying to prove theorems, and then you can try to classify, like what are the different ways a particular fusion category could act on the lattice? Or how many of them are there? Is there only one kind of canonical way? Like is that example that we all know and love the only example up to some equivalence relation? And those kind of questions, it turns out, are really, really hard to make precise if you just work on like periodic boundary condition spin chain because essentially, from a mathematical perspective, everything looks the same in finite dimensions. So you somehow need to go to the infinite volume so that the structure kind of pops out. And so that's really the motivation for doing these sort of things is that you can treat things model independently and try to prove classification type theorems. Okay, so to start, I just want to give you so I'm not sure with this audience how many people are familiar with the kind of mathematical formalism that mathematicians usually use when we work in infinite volume. So I just want to kind of briefly review that. So let's talk a bit about infinite volume. The star of the show is this so-called quasi-local algebra. So it's just the infinite tensor product of D by D matrix algebras, but you take the tensor product over all the sites in the lattice. And so this is a big infinite dimensional algebra because I have operators localized at all the possible sites in the lattice. But the key is that for every interval, there's a special finite dimensional subalgebra of operators localized in that interval. So this algebra A has some structure. It has, I have these special subalgebras called the local algebras, and the local algebras are all finite dimensional. They're just tensor products of matrix algebras, right? This is just the tensor product over I of these D by D matrix algebras. Okay. Now, the key thing that's weird, I think, for many physicists when mathematicians start talking about this infinite volume limit picture is we don't pick a Hilbert space to start with. Okay, we don't have everything acting on a particular Hilbert space. And the reason why is this whole sectorization issue. There's different ways to put these operators on a Hilbert space. And when you pick one to begin with, you're kind of like tying your hands behind your back and you can't see other Hilbert spaces that you might care about. So instead of working on a Hilbert space, you can axiomatize states abstractly just as positive linear functionals. So these are functions from this quasi-local algebra to C such that positive operators get positive numbers, and I normalize it a little bit. And you should physically think of this as just telling me what are the expectation values of all my observables, right? If I'm thinking of these operators, the self-adjoint ones are the observables, and I'm just telling you what the expectation value of this state is for every single observable. And that's equivalent to having the information about what the state is. And so you have the state space. S of A is the state space, and it's not a Hilbert space, right? It's a topological space. Actually, there's multiple different topologies. It's a convex space, so it has like mixed states and pure states and everything all in there. And it's a rather complicated looking object. It's not something as simple as like density matrices or something like that. And that's to be expected because it has all these different phases and stuff in there. All that kind of structure is supposed to be embedded somehow in the structure of this space here, the state space. But do not fear because Hilbert spaces are never far away. There's always this GNS construction, which does the following. So given a state you can always build this Hilbert space H sub phi with A acting on it. And basically, what this Hilbert space looks like is you take the state and you kind of like formally apply local operators to it. And so you kind of take all the little local perturbations of the state and you assemble it into one Hilbert space object that A acts on. And it's somehow the minimal Hilbert space representation of A that contains a vector state associated to your abstract state that you care about. So this is kind of like the minimal way to represent your state on Hilbert space. But the point is, so you can always grab a Hilbert space when you need one, but you don't start with a Hilbert space. And this is actually really important for lots of technical reasons, because when you start with the Hilbert space and you only look at operators on that Hilbert space, you're missing a whole bunch of stuff. And we'll come back to that a little bit later. In particular, like non-local operators. We care about non-local operators. Usually, if you were a physicist working on a Hilbert space, a non-local operator would be an operator on the Hilbert space that does blah, 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 blah. But then your non-local operator can't change sectors. You can't change your Hilbert space to a sector you don't know about because it has to act on the sector by definition. And so there's all kinds of stuff that we'll get to later. But okay, so this is the basic setup. You also have Hamiltonians. They're not going to play a big role in my story today, but
Sorry,
you
can I
you
ask a
also can.
question?
Please do.
Um, but so if you demand some extra condition about the algebra of operators, some notion of maximality, for instance, something like Hug duality, don't you get a unique Hilbert space that does the
Um,
job?
no, no. So are you thinking about like in algebraic quantum field theory where you have Hog duality and a Hilbert space representation? Um, So if your if your space is like a circle, so in like conformal field theory, when you have like a chiral conformal net, then no, there's not a unique Hilbert space because you have super selection sectors. But if you put all the super selection sectors and the vacuum sector together into one Hilbert space, that is usually good enough. But here we're infinite volume, and so you have many different representations that all satisfy Hog duality. Somehow, like the quantum field theory that you may be thinking of is emergent in a given Hilbert space representation. But this is like before I pick a quantum field theory. There and different kind of quantum field theories could emerge as different phases of the same kind of spin chain is the idea. So yeah, you're pre-quantum field theory in that sense. But yes, in the context of algebraic quantum field theory, usually there's like a distinguished Hilbert space representation. That's the vacuum, and you can do everything in terms of that. But we're kind of pre that.
I
We're
see.
before.
So if I understand correctly, what you're saying is that if you fix the algebra of operator, even if you demand this algebra to be maximal in some sense, at the level of the Hilbert space on the lattice, there might be several Hilbert space corresponding that gives exactly that algebra as maximal algebra. But all these Hilbert spaces in the thermodynamic limit, when you look at some QFT description, they will give you the same answer.
Not quite. I don't think that's quite right because,
Uh-huh.
yeah. So first of all, different. Like for example, I like this. Like I could pick one of these. Like I can just have completely inequivalent representations of this algebra. Let me just put it that way. And in all of those out, and they're irreducible, right? I can have two irreducible representations that are just not equivalent as
Sure.
representations. There's no unitary intertwiner. So let me just say that. And they don't all give me equivalent stuff. Like I have different phases. That's what different phases are. Or I mean, that's not only what they are, but in particular, the inequivalent phases are inequivalent representations of this algebra on Hilbert space. They're also inequivalent in a weaker, or I guess I should say inequivalent in a stronger sense, but they're in particular not equivalent as ways of putting it on the Hilbert space.
I see.
So there really are very, very different ways of sticking this on Hilbert space.
Okay.
Now, locally, it's just you can use the same Hilbert space always. It's just there's no infinite volume limit Hilbert space. There's no such thing as the infinite tensor product Hilbert space. Or let me put it this way: there are many such things as the infinite tensor product Hilbert space, and the different choices give you different physics. And so you don't want to pick one unless you know what physics you're doing. And if you know what physics you're doing, like if you know what the ground state is supposed to be, then you can go ahead and build your Hilbert space. You can construct your infinite Hilbert space that's based on that ground state, for example. But if you don't already know what ground state you're working with, you don't want to pick one of these infinite volume Hilbert spaces because you want to compare different ones, right? I want to understand phase transitions. I don't want everything being on the same Hilbert space. I want to be able to look at different ones.
Yeah, thank you.
That's
Okay, I understand. Thank you.
basically. Yeah. Okay. And then when you have Hamiltonians, but again, the Hamiltonians today aren't going to play a major role in the story, but you can make sense of them in this picture in the same way you usually do. Just instead of being sums of operators on a Hilbert space, they're just sums of operators in this algebra. And they're formal sums. They don't actually converge to anything, but it's fine. You can still treat them in the same way and talk about ground space also. Okay. So now let's get to SymTFT. So I actually learned SymTFT from a subset of you all last year at KITP. So I don't think I need to explain SymTFT too much, but the basic idea, just to review, this is a time slice picture. If I think of this A as being a 1D theory, then if I had a SymTFT decomposition, right, I would have this physical boundary, B phys, I would have this topological boundary, and a fusion category of defects acting on the topological boundary, and this T in the middle is supposed to be some one-dimensional higher topological quantum field theory. Okay, so the starting point of this whole framework is the observation that I can think of the operators localized near the physical boundary as being a subalgebra of all these operators. So in other words, if I set B to be the algebra of local operators localized near the physical boundary, then B should be a subalgebra of A, right? In a more down to earth terms. If you have a symmetry, this B is just the symmetric operators. But in the SymTFT picture, it's the operators localized near the physical boundary. Okay, and so the goal is to say, so if I'm in this abstract situation where this A is just the tensor product of matrix algebras, so given B subset of A, when does it come from a SymTFT decomposition? So when does it come from SymTFT? And in particular, can I extract all the stuff, the bulk, TQFT, the fusion category, all the stuff? Can I abstract it just from this subalgebra? And so the goal is going to be to define some conditions. And when a subalgebra, we'll call it a physical boundary subalgebra, is the physical boundary subalgebra of its SymTFT decomposition, and how you can kind of pull out all this stuff from that. Okay, and that's the basic idea. So if we forget about A for a moment, so
Quick
forget A
question.
for yes.
In this inclusion, A is still the infinite tensor product. It's not like one of the represented algebras.
Yeah, so A is an infinite tensor product. So you can also, so A doesn't have to be an infinite tensor product. This is actually very general. A can be any net of algebras over Z in some sense. But yes, like in applications, it's the infinite tensor product. Or, if you're trying to represent some fusion category that is not integral and it can't act on tensor product Hilbert space, maybe this is like the local algebra, the quasi-local algebra associated to an anion chain. So you can make it a little bit more or less easy. Instead of doing a tensor product, you could do an anion chain, which means your local operators, instead of being all local operators on the tensor product Hilbert space, they would just be the ones that map, coherent chains to coherent chains and preserve boundary conditions, and then you take a limit of those. And so A doesn't have to be tensor product. It could be anything. In particular, it could be these anion chain algebras. But yeah, sure, think of it as tensor product for now, in particular. But the key point is that B, this subalgebra, is very, very much not in any situation. It doesn't factorize as tensor product. B is much more interesting and complicated, these physical boundary subalgebras. Okay. But A is, yeah, A is just something like, if we're doing it really symmetry on the lattice, it's the tensor product algebra. Okay. And so let's forget A for a second. And so let's forget the top part of the SymTFT decomposition. So I just have T and I have this B here. And the question is, how does B see T? Like, are there ways we can try to talk about what the bulk TQFT is supposed to be just in terms of this algebra B? So that's kind of the first question to ask before we can answer this original question. So how does B see T? Okay, and the answer, or an answer, I guess I should say, is through the string operators. So if I take a string operator given by some anion, the string goes off to infinity because I'm working in infinite volume limit, and I have some interval here I can push this onto the boundary, right? And I get actually an operator that's localized near the boundary, but it's not a local operator. So this is non-local because the string is popping off to infinity, but it is localized. That's the key point. Localized in the interval I, right? Which means that basically if I take any operators localized outside I, it's going to commute with it, right? Because that string is often the bulk. So if I take operators localized near the boundary that are outside of this interval I, they're going to commute with this string operator that I pushed onto the boundary in I. So there's a sense that the string operator is localized even though it's non-local. It's not one of the local operators that's just sitting there localized near the boundary. Um, and the other key point is that not only is this thing localized in I, but I can apply local operators and move where it's localized, right? That's the condition that the string operator is topological, is that you can apply whatever little unitaries and move it around, right? So in particular, it's movable. Movable to any I with local ops in B, right? That are localized in B. Okay, so these are the three conditions that I think kind of like characterize the kind of things in terms of B, what kind of operators we're talking about that should correspond to string operators from the bulk. So what we're going to do now is come up with an abstract mathematical axiomatization. If you give me an algebra B with these local subalgebras defined for every interval I, I'm going to define for you a braided tensor category of these non-local, localizable, movable operators. And it's going to be called the category of DHR bimodules. And it's going to be a braided tensor category. And the proposal is that if you give me an abstract algebra B with all these little local subalgebras defined by intervals, that thing is supposed to live on the boundary of a TQFT, where the TQFT is determined by what the DHR bimodules are, the braided category of DHR bimodules. Now, the braided category of DHR bimodules would have to be the right kind of braided category to give you a TQFT. In particular, it'd have to be a Drinfeld center of a fusion category if you wanted to do the SymTFT game anyways. But it turns out that fairly generically, these DHR bimodule categories are always Drinfeld centers, which is another theorem that I'll talk to you. So everything's looking good. So what I'm about to do now is drop some mathematical structure on you, but the motivation is to try to capture these string operators. Now, the first thing to notice is so now I guess I'll say we have so given abstract B. And we also have these BIs, these subalgebras for every interval in Z. So I have this kind of abstract algebra, but I also have this local structure. And you can write down some axioms this has to satisfy that look very much like algebraic quantum field theory axioms. But you basically have an abstract, discrete algebraic quantum field theory. But for our purposes, we just have this algebra B and these local subalgebras I that generate it. So what are the non-local operators here? And so here's kind of a formal definition. A non-local operator is a completely positive map from B to B. So I'll tell you what that means in 1 second. Completely positive. You may be familiar with this term from quantum information, from B to B. So what does completely positive mean? So this means that if I take phi tensor the identity n from B tensor matrix algebra over C to B tensor matrix algebra C, so in other words, I tensor on some ancilla, and I take this map that's mapping from B to B, and I think of it as mapping from B tensor my ancilla algebra to B tensor my ancilla algebra, this should take positive operators to positive operators for all n. So this should map positive ops.
Corey, are you making any assumptions about what this does to the net structure, like for the interval subalgebras?
No. So there will be some assumptions coming later, but in general, a non-local operator doesn't have to preserve locality or anything. You could have locality preserving non-local operators. That's a kind of non-local operator, but this general form of a non-local operator is just wildly general. It can do anything, right? It's violently non-local in some sense. It could be violently non-local. Eventually, we're going to get to ones that are localized, which behave in a very controlled way on the net structure. But right now, it's just super general. So it should map positive to positive ops for all n. And that's what this completely positive is. If I removed this ancilla condition, I would just have a positive map from B to B. But because you want to always be able to tensor with ancilla and stuff, completely positive, it turns out, is kind of like the right notion of this generalized operator. And this is still an operator in the sense, like, what is an operator supposed to do? Well, if I have a linear operator on a Hilbert space, it maps a state to a state, right? You apply an operator to a state, I get a new state. Like operators should map states to states. And indeed, these can map states to states. If I take a state in the state space, I guess I'm working on the algebra B now, then I can send this to phi composed with psi. So I do psi, which maps B to B, and then I apply the state, which is, remember, it's just a functional. And that gives me a new positive linear functional because psi is positive. And so actually this acts on the state space and it can move states all around. So it still like has the feel of an operator, even though it's a much more abstract sort of gadget. Okay, so it still acts on states. Now, the thing that's interesting about non-local operators is they kind of, if I take a non-local operator, I could pre-compose with local operators, and I can post-compose with local operators, and I get a whole bunch of other non-local operators that are kind of related to each other by these local perturbations. Okay, and so what you can do is kind of just like we took a state and when we did the GNS construction and we took all these local perturbations and they glommed together to form one Hilbert space sector. You can take a non-local operator and put all the local perturbations of this, and they glom together to form a bimodule actually over the algebra B. So let me explain how this works. So the idea is that like local perturbations of psi assemble into an interesting structure. It's what's called a correspondence is the official term in the math literature, but informal a little bit more informally, it's a BB bimodule. So literally a bimodule over the algebra B. So a BB bimod with a B-valued inner product. So it has an inner product like a Hilbert space, except the value of the inner product is in the algebra B. So let me explain how this works. Okay. So what I'm going to do is I'm going to take a non-local operator described by one of these CP maps, and then I'm going to build one of these BB bimodules with the B-valued inner product. And you should think of this as like a glomming together of it's like a sector of non-local operators. Okay, that's the basic idea here. So what do we do? So let's define x tilde to be the span, the formal span. So this is formal stuff. So I'm just writing formal linear combinations of things that look like this, where B1 and B2 are in B. And this vector omega sub psi is just like a formal vector. I'm like formally writing down these symbols where I take sums of B1s, omega psi, B2. And then what I'm going to do is define a B-valued inner product on this thing, and I'm going to quotient by the kernel. So let me take the B-valued inner product of B1 omega psi B2 with C1 omega psi C2, and I'm gonna write this subscript B so that we remember this inner product is valued in B. What's the formula for this? Well, it's going to be B2 dagger psi of B1 dagger C1 C2, and of course B1 B2 C1 C2. Everything lives in B. And psi, right, maps B to B. So this lives in B, this lives in B, this lives in B, this whole thing lives in B. Okay, and so this is a B-valued inner product. And then but there might be some things that give you zero. Like I could take something B-valued inner product with itself gives me zero. That's not good because I want it to be more like a Hilbert space. So what I'm going to do is quotient by the kernel of this form, which just means you basically kill all the stuff whose inner product with itself is zero. And then you maybe complete this in some kind of B-valued inner product topology to make it more like a Hilbert space. And what you get is a correspondence called X. And so this is a BB bimodule because I just act on this from the left and right. Like at the level of formal linear combinations, I just stick B elements on the left and B elements on the right. And you can check that it's well defined on the quotient. Okay, so I get a BB bimodule, but it comes with this B-valued inner product. Okay, so given any abstract correspondence, so now suppose I started with an abstract correspondence, which means just a BB bimodule with a B-valued inner product X. This defines, each element here defines a non-local operator in the following way. You define phi sub X of A to just be the inner product here. and this lives in B, right? So vector or what do they call this? Matrix coefficients from the correspondence actually are non-local operators instead of being states, right? Instead of giving you an expectation value on all the observables, it's giving me a non-local operator that maps B to B. Okay, and given one of these non-local operators, like when you build one of these things, you're really just kind of taking all the local perturbations and you're glomming them in together to make a sector. And you have the thing you get out is a generalization of a Hilbert space. In fact, if you pick instead of doing BB correspondences, if you did BC correspondences where C is the complex numbers, you just end up with Hilbert space representations back. So this really kind of generalizes Hilbert spaces in a particular way, this whole like world of correspondences. But you should think of a correspondence as just like a sector of non-local operators. That's what one of these gadgets is. And the data of how it transforms under local pre and post composition with local operators. Okay, so that's how you should think of one of these things. So you can define a category called core of B. This is a C star tensor category because fundamentally these correspondences are bimodules, right? There's a left action of B and a right action of B. And whenever I have two bimodules, I can take their relative tensor product, where I take kind of the linear tensor product and I quotient by this action of B in the middle. So with tensor prod given by x box times over b y. And so you take the algebraic tensor product of these bimodules, and you can always put a new inner product on that. There's kind of a canonical way to make that a new inner product. And roughly speaking, there's a precise sense this is true. This corresponds to composing non-local operators. Because if I compose two non-local operators, they're CP maps, I get a new one. The composition lives inside this correspondence. Okay, this has stuff. Okay, so anyway, okay, so again, we haven't used any of the local structure. This is just something about C-star algebras associated to a C-star algebra is this tensor category of correspondences that you should think of as, if you're thinking of your algebra as the local operators or quasi-local operators or whatever. Then this correspondence is like the non-local operators, but they kind of glom together into these sectors, and those sectors form a tensor category. Okay, that's what's going on here, if that makes sense. Okay, so now let's return to the original thing. Let me just go back a couple slides.
Can I ask a quick question before you move on?
Oh,
from
yes.
here? I didn't understand when you talk about taking the completion with respect to this B-valued inner product. I know what that means for a C-valued inner product because there's like a norm topology, but what are you talking about here?
So B is usually, when you do this game, I've kind of skipping over some technical things. B should probably be a C-star algebra. And then you can define the norm of something by taking the B-valued inner product and then taking the norm, but since this is covariant, you probably want to take a square root. But this is the norm in B, because B is a C-star algebra, so it has a norm on it. This is like the matrix. If B is made out of like a matrix of matrix algebras, there's take the operator norm on the matrix algebras. That's the norm I'm talking about. And so there's a unique norm on B. If B is made out of finite dimensional C-star algebra, so out of multi-matrix algebras, in other words, there's a unique norm on any kind of limit of these things. And so you can define the norm of X to be equal to that, where this is the norm in B, and then you complete with respect to that. Does that make sense?
Yeah, all good.
Okay. Yeah. I've been purposefully like de-emphasizing structure on B to because in practice it's some subalgebra of tensor product and matrix algebra, so you don't need like the abstract structure, but there is a whole abstract theory sitting underneath this stuff. Yeah, good question. Okay. So and I should mention that the completion is not that essential because in all the actually the completion is essential. Never mind. Okay. But anyways, yeah. So let's come back. So we want to try to describe like a string operator associated to an anion type. If I push it onto the boundary, I got a non-local localized operator. But remember, this third condition said I could move it around anywhere I wanted with local perturbations, which means that I should be able to get an operator localized in any other interval inside the same kind of sector of non-local operators. So in other words, inside the same correspondence. So what we're going to do is, instead of directly axiomatizing the string operators that are pushed onto the boundary, we're going to axiomatize the sector of string operators that corresponds to this one string operator. Because there's not really one string operator. The string operator comes in a family because I can move it around everywhere, right? There's really a sector's worth of string operators in this sense that I'm talking about. Okay, good. So let's go back and try to do that now. So definition, if X is a correspondence, so if it's element of correspondence of B, I'm going to define this. This is going to be the set of, if I'm thinking again of vectors in my correspondence as non-local operators, this is the set of non-local operators localized in I. This is what I mean to be localized in I. And this is going to be the set of elements in X such that it commutes. Remember, X is a BB bimodule, so I have a notion of left multiplication by B and right multiplication by B. So, but I'm asking them to agree for all B that are localized in B sub Z takeaway I. So it's in the complement of the interval I. So I take all the local operators localized in the complement of I, and I take all the vectors in my bimodule that commute with all of those, and I'm going to think of them as being localized in I via some, there's no Hog duality, but if there was Hog duality, this would be like, oh, Xi like is the commutant of the stuff localized outside. It's like a Hog duality type thing. Okay, so I'm going to define that to be X. This is my definition of Xi, and now another definition, a correspondence is called a DHR bimodule. A DHR bimod. If for all sufficiently large intervals, and what that means is like there exists an R such that for all intervals whose size is at least R. Okay, and that's what I mean by sufficiently large I. If I take Xi and I do local perturbations on the right, which correspond to post-composition. If I'm thinking of this as composing operators, multiplying on the right means actually do like first do the local operator in Xi and then do some local operator in B. So if I take all the post-compositions, this is actually the whole bimodule. Okay, so in other words, if I take the stuff localized in I and then I apply local operators to it, I get everything else in the bimodule. And this is for every I can do this. So that means that I can localize, I kind of have a generating set for the bimodule as a right module localized in any little interval I want to. Okay? And that's it. That's the definition. Okay? So we'll call this category DHR of B. Okay? And this is a C star tensor subcat. Just by that, you can check that if I take two of these things and I take their relative tensor product, it again satisfies this condition very easily. So it's a C star tensor category. Good. And now the theorem is that this was a bit more blood, sweat, and tears. But the theorem is that, so here you have to make an extra assumption on B, which is kind of like a Hog duality type assumption. It's a little bit different from Hog duality because we don't have a Hilbert space. It's what's called weak algebraic Hog duality, but I'm not going to write it down. Just some technical assumption that's satisfied in all the examples. But I'll just say this anyway. So DHR of B is a braided C star tensor category. So it's like a braided unitary tensor category. C star tensor category. And it works just like you think it should. How do you make a braiding in the anion picture, right? Like if I had two string operators, if I had like A and B, their tensor product is like composing them. How does braiding work? Well, you just move them around so that they're not like sitting right next to each other, not on top of each other. And then they just kind of commute because they're localized in different places. And then you can kind of push them back if you want to. And that's how the braiding works. And so you can kind of do that at this level of DHR bimodules. It's just, it's just a lot of annoying technical work. But it's a braided C star tensor category. And this is very similar, if you're familiar with algebraic quantum field theory, to the DHR stands for Doppler, Haag, and Roberts super selection theory, where you build the super selection sectors of your algebraic quantum field theory. This is very similar in spirit, though technically it's different. You have to do different, like the arguments, you have to do different kind of arguments and stuff like that. But it's the same idea. Like this is where the idea came from, was Doppler, Haag, Roberts super selection theory and AQFT. Okay, but anyways, okay. So the proposal is that well, let me put it on a new page maybe. Proposal, kind of like red, uh, is that if B is abstract net of algebras, say, or has that local algebras of if B is abstract net of algebras on Z, then DHR of B describes the bulk um, V. I don't know if V or A is the right word. Bulk. I think it's V because it's determined by DHR. Bulk TQFT that B should be the boundary algebra. Should be physical boundary algebra. Okay, and so that's the claim is that this is how if going back to the original situation where I have a SymTFT decomposition and I have my B sitting here, then the claim is that the DHR bimodules for B should be the anion theory for the bulk thing. Okay, that's the claim, the proposal. And in all the examples, this is what happens because here's the next theorem, is that if B is symmetric operators under, really this applies to any categorical symmetry. So as formulated with MPO or weak Hopf or whatever, or group or Hopf or whatever, under C symmetry. So if C is the underlying fusion category for this symmetry, then the DHR category is the Drinfeld center of C, as you expect. Oh, okay. And this was actually this is the the theorem that this is braided, and I should say this paper came out a while ago. This was late in 2023 that this was braided, and the same as this. But the real hard part of this was actually showing that the abstract DHR category, which is defined super abstractly, right? You give me an algebra, and I have to find all the bimodules satisfying this condition to prove that that actually is equivalent to the Drinfeld center of C. Is you have to use a lot of subfactor theory, so it's pretty technical. But in any case, this is like proof of concept that maybe this is a good idea to do it this way. It's giving you the right answer in the case, like in all those examples in the lattice and things like this using MPOs, it ends up working. Okay, good. So let's go back now. So any questions? Let me stop here. Interrogate me. Yeah.
I have a question, Corey. So usually when I think of SymTFT, I usually think of the topological boundary as being the more important thing than the physical boundary. But the topological boundary, I don't think it's even been mentioned yet.
No, it's not
So
been mentioned. So that's coming next. Yeah. That's coming next. But
okay.
but exactly kind of the point, like from our point of view, is actually the physical boundary is more important. And I would argue actually that even in SymTFT, the physical boundary is more important. It's just that you can slice off a piece of information about the whole theory, which is like the fusion category part, and you kind of like squeeze out the interest, like the remaining interesting bit, which is the physical boundary. So I would almost argue the exact opposite of what you said. I mean, I know what you're saying for sure. Like,
Mhm.
indeed, topological boundary is the part that we like argue about it with, or like that we do stuff with. But it's like the part of the theory that's really going on that's essential now is the physical boundary, and then I can do all these TQFT arguments, using C. Really, I would say most of the arguments are really about the TQFT in the book.
Hmm.
But our claim is that TQFT is tightly tied to this physical boundary in the sense that the physical boundary determines just as an abstract algebra determines what the bulk TQFT has to be, and then we'll see in a second that where the symmetry boundary or the topological boundary comes from. Yeah, in this context, yeah, it's coming. But I think exactly de-emphasizing the topological boundary is important here because there's all these different ways that people talk about symmetries, right? People are like, oh, I have a weak Hopf algebra symmetry. I have a Hopf algebra symmetry. I have an MPO symmetry. Like, oh, my MPO symmetry has to satisfy all these conditions. Like, I don't really know, like if I'm a mathematician trying to prove theorems about symmetry, I have to pick one of these frameworks. And like, yeah, maybe I can go between them, but it's still really annoying for me. But this says, actually, I don't care how you wrote down your symmetry. I just care about those symmetric operators because whatever kind of symmetry you're going to write down is going to have some symmetric operators, and I can do my whole analysis with respect to those symmetric operators. So I don't really care how you write down your symmetry. And in fact, there's kind of a canonical form that we're going to recover in a second of what that symmetry looks like in the end. So it's coming for sure. Yeah, we don't want to throw the baby out with the bathwater. But it's not clear to me if the fusion category is the baby or the bathwater. I don't know. Yeah. Okay, good. Okay, great. So next. Yeah, okay. So let's go back to the original situation. So back to the lattice. And I should say that actually everything that I just said doesn't really care that you're on the lattice. You could be on R, and in fact, the DHR by modules works on any metric space that's coarsely equivalent to Rn for some n. But it's going to be a symmetric category in high dimension. So this is really interesting in one dimension. But you can also do this over R. Like you can do this for continuum theories. And indeed, there are people who've been thinking about similar sort of things in the context of, chiral conformal field theories. Again, they tend to use more the super selection, the OG DHR perspective. Because the local algebras are very different. But this story is like really a generic story. It works on the lattice and in the continuum, although I'm focusing on the lattice here. Okay, so back to the lattice. So I have B inside A. So the key point here is that this big algebra is a BB bimodule. Okay, so actually it's a correspondence because an additional piece of data that we have is when we have these symmetries is we have this averaging operator that it's what's called a conditional expectation, but it projects A down to the symmetric part B. You can think of it as like projecting to the symmetric sector, but just at the level of operators. And so, for example, if you're acting by group symmetries, and they're acting by automorphisms of the algebra, you conjugate by the unitary, this would just be sum over all the group elements divided by the size of the group. Or if you're acting by Hopf algebras, this would be like the Haar integral element or something like that. But there's some kind of projection onto the symmetric part that kind of comes as part of the data of your symmetry. And so you can use that to put a B-valued inner product on here. So I can define an inner product, a B-valued inner product, by just doing the E of A1 star, or sorry, I'll use daggers for this talk, A2, and that lives in B. And so this, and it's already complete. You don't have to do any completions or kernels and stuff. So this is a DHR bimodule, it turns out. So in the symmetry setting, in all the cases, this is a DHR bimodule. But more than that, it's an algebra object in the category of DHR bimodules. Where's the algebra structure come from? Well, A is an algebra. So if you just use the multiplication on the algebra, it actually gives you an algebra morphism in the category of DHR bimodules and turns A into an algebra object inside this abstract tensor category of DHR bimodules. So it is an algebra object in DHRB. Okay, and more than that, it is also Lagrangian. And so what I mean by it is these things is that in all the examples, it is these things. Okay, so let me now give you a definition. A subalgebra, again, A is the big quasi-local algebra. A is like a tensor product of matrix algebras or an N-yon chain algebra or something. But a subalgebra, B inside A, is a physical boundary subalgebra. Boundary subalgebra. If A is in DHR of B, is a Lagrangian algebra, which in particular implies that DHR of B is the Drinfeld center of something, i.e. DHR of B is the center of C, where C is just the category of A modules. DHR B on A. So basically, when I have a subalgebra, I can go calculate its DHR bimodule category, and I can think of my big algebra as an algebra object inside this category of DHR bimodules. And I can say, okay, is it Lagrangian? Yes. If it is, then this is what I'm going to call a physical boundary subalgebra. If it's not, well, then it's just an interesting thing, but it's not. It doesn't come from a SymTFT decomposition. Okay. And so why is the Lagrangian algebra the important bit to get the SymTFT decomposition? Well, how do you describe a topological boundary condition of a TQFT in 2 plus 1 dimensions, you pick a Lagrangian algebra. And so this Lagrangian algebra is telling you what the topological boundary is supposed to be. Okay. So and this is where your fusion category pops out. It pops out as the local, or not the local modules, but A modules inside DHRB. So this Lagrangian algebra is telling you what the topological boundary condition is, and this C is the symmetry category. Now, I won't go into it because yeah, I should ask, how long is the seminar? How long are the talks usually?
The
Usually
1
like
hour.
about an hour, but
1 hour. Okay,
it's okay if you
good.
go a little bit over.
Okay, cool. So I got some time. But so in the interest of time, I won't go into all the details, but it turns out that you can realize the objects in the fusion category as certain kinds of non-local operators on A, right? Because the DHR category was all about non-local operators on the symmetric subalgebra B, but you can, as you should expect, realize the fusion category as non-local operators on the big algebra A. And in fact, there's a DHR type condition. You can look in the paper where we do all this, but it's not super important. But you can get all that symmetry category stuff that you would expect out of it. It all comes out and it works. And the paper that I'm talking about is the paper with David Evans that it's called like an operator algebraic approach to fusion category symmetry on the lattice, where we kind of do this whole SymTFT stuff. Okay.
I have a
So
question about this.
yes.
So
Yes.
B, so did I follow correctly that I should think of B as the subalgebra of A that is symmetric under whatever your symmetry is?
Exactly. Yeah.
Good. And then so my question is it okay if B has no local operators?
No. Yeah. So then it wouldn't be a physical bound. I mean, so it depends on how you use the word physical boundary. But no, it's not okay if B has no local operators because B has to remember the whole SymTFT decomposition. However, you can talk about boundary conditions by taking states on B. These are the symmetric states. And you can have topological boundary conditions because I'm anticipating you wanting to glue on a topological boundary condition on the bottom. Yes.
So sorry, I guess I mean like I'm given some A, and let me just
Mhm.
think of like ordinary symmetries. So these are some like algebra automorphism of A.
Yeah.
I can definitely think of like very, very simple algebra automorphisms that has no invariant local operators. They're all non-local.
Yeah.
Like for example, like the simplest one is like lattice translations. Like
Yeah, exactly. So that one doesn't count as the kind of symmetry that I'm working in. So what I would say is
I see.
that the symmetries that fit this framework are finite internal symmetries, and I would describe
Ah,
those ones as kind of external symmetry
I see.
in this sense. So we are essentially working under the assumption that this physical boundary algebra has to remember the bulk TQFT. And if there's no local operators there, it remembers nothing about the bulk SymTFT. So this framework would not apply to something like lattice translation. This thing applies to stuff like MPO symmetries,
Mm-hmm.
Wyckoff algebra symmetries, finite Wyckoff algebra
Hmm.
symmetries. It doesn't work well with discrete groups.
Yeah, it seems like the
Now, it
finiteness is
can work with
important. Yeah.
it can work with compact groups, but you have to do
Mm.
some stuff. You have to make your local Hilbert spaces infinite dimensional. Otherwise, it kind of like it can degenerate in a certain sense, and you miss some of the bulk TQFT just because the bulk TQFT for rep G, where G is a compact group, is much more complicated than that. It's not the Drinfeld center of finite dimensional representations. It corresponds to the Drinfeld center of infinite dimensional representations. So you have to kind of locally throw in infinite dimensional ancilla everywhere. And then it actually does work in the compact group case, although that's not written up yet.
Mm.
But yeah, so this is like, think like finite
Mhm.
plus internal symmetry.
Okay, thank you.
Yeah. Good. Yeah, great question. Okay, good. Okay, so what sorts of stuff do you want to do? So you would like to do some kind of classification. And at the moment, classification, I don't have any kind of like concrete answers, but you can prove the following theorem. So if you accept this formulation of like what counts as a finite internal symmetry as something that has a SymTFT decomposition, and then you believe my story about what SymTFT decomposition should be, then you can say when certain things can have them or not have them. And so here's an example of a theorem. C. So if C is fusion, C is realizable on a tensor product quasi-local algebra. So on a tensor product. So one of these infinite tensor product things, quasi-local alg, if and only if C is integral. So of course, I think the standard thing here is if C is anomaly free, so it has a fiber functor, then you can just realize, take a Hopf algebra, act on every site, realize it on site, and boom, you got it. You realize your fusion category symmetry by using Hopf algebra stuff. But it's known that you can also have integral fusion category, or like for example, Vexy2 omega can be realized not on site, but you can realize it with locality preserving automorphisms with Z2 omega, and that has an anomaly. So the question is, what's the general class of things that can actually act on tensor product stuff? And the theorem is, first of all, it has to be integral, and you can use this framework that we have to prove that it has to be integral by using some K-theory abstractions from the theory of C-star algebras and stuff like that. But you can also go the other way, and if it's integral, you can build this thing acting on a particular kind of anion chain and then conjugate that anion chain into a tensor product thing with a bounded spread isomorphism. And so you can actually realize any integral fusion category on some tensor product anion chain. Now, I'm not saying you can realize it on every tensor product anion chain. Like, for example, you may not be able to realize it on qubits, but you can realize it on qubits for some d. And you can, so that's what I'm saying here, just to be clear. I'm not saying you can realize that on every anion chain or every tensor product Hilbert space, but you can realize on some. And so that's like a nice thing you can do with this formulation now, is you can start proving theorems like this. Now now you have to believe me that this is a good definition of what it means to have a fusion category symmetry, but it covers all the examples in the literature. All the examples in the literature fall under this heading. So I think it's pretty good, and I think it's conceptually motivated. I don't know. So anyway, yeah. So if you believe that, then this theorem is a consequence. That's the first thing. The second thing is I want to do, I was really inspired by papers that came out of your group, the categorical Landau paradigm. I like that conception of what's going on here. And the idea is that, okay, that symmetric gapped phases are supposed to correspond to Lagrangian algebras in the SymTFT. In other words, they're supposed to be topological boundaries that you glue on the bottom, right? But how do I make sense of that? Like, what do I mean by topological boundary in this framework I have? Because I have this big algebra A and I have this subalgebra B, but I don't see, where's the room for what do I mean by a symmetric gap phase? And so the way you can deal with that is that you have a bijection between symmetric states on A and just arbitrary states on B. You can use this. So if you have a state on B, which is the symmetric subalgebra, you can apply that averaging operator, that conditional expectation, and pull back the state to get a symmetric state on A. Conversely, if you have a symmetric state on A, you can restrict it to B and pull it back, and because it's symmetric, you get the same state back. So actually, there's this kind of symmetric states on A are just ordinary states on B. Okay. So you can kind of work on B and forget about A for a moment. And if I'm just worrying about like boundary conditions, right? Because B doesn't know about A. It knows about the bulk SymTFT. It doesn't know about the topological boundary. B just knows about this bottom stuff. But that's what we need to focus on anyway to talk about boundary conditions that we're trying to glue on the bottom. So this kind of formalizes that the states that you care about, they're just states on B. You can forget about A for now. Okay. Then what you can do, so let's let phi be a state on B. You can do this GNS construction, which gives you a Hilbert space representation of the algebra B. Okay, and from this you can build an algebra object in the TQFT category as follows. You basically take your DHR bimodules and you tensor them on so this Hilbert space is a left B module because the B is acting by operators on here. X is a BB bimodule, so when you do this tensor product, you get a new left B module. And so you can take this category of things where X ranges over DHR bimodules, and this is a module category for DHR. And remember, DHR is supposed to be the bulk anion theory. DHRB is the bulk anion theory. So now I have a module category. You can take internal Hom, just like you do in category world of the special object is this GNS representation. this gives me an object in alg of dhr of B. And now I can say, okay, well, I'm going to declare such a state to be, saying the word gapped is a little loaded here when I don't have a Hamiltonian. What do you mean by gapped state? What I actually mean is that this is a topological state. It's a topological boundary condition. Again, if this algebra is Lagrangian. So this is, again, a definition, but phi is topological. It corresponds to a topological boundary condition, but I'll put it in quotation marks, okay? It's topological in the sense that if you do any RG flow, this is really going to correspond to a topological boundary condition from general. But anyway, so phi is topological. If this algebra, let me give it a name. Let me call it actually A phi. A phi equals that. So this is topological if A phi is Lagrangian. Okay. Otherwise, I mean, you still get so this also for a gapless state, you get, this is how you can get those, the commutative algebras and stuff that you care about that describe gapless states. It's sitting right there. You just take internal Hams of this DHR module category. That's the commutative algebra you care about when you're doing gapless stuff. You can the recent mixed state stuff that some of you and other people have been doing, you can also formulate in this way. So you can kind of make all of that stuff into this formalism by using this picture. And then so here's a theorem. Is that if phi is a topological symmetric state, then when I take phi and think of it as a state on A, then phi decomposes as a sum of these phi I, where phi I are pure, and are in bijective correspondence with the simple objects of the associated module category. Which is very, this is very much inspired by the categorical Landau, one of the categorical Landau papers that you all have. But anyway, are in bijective correspondence with simples in the module category M phi that's associated with the Lagrangian algebra A phi, right? You have this A phi. It defines a module category over C because it's Lagrangian. You take the simple objects. Your symmetric state will actually decompose as a convex combination of these pure non-symmetric states. Like these are not symmetric. This is symmetric, but it's like in general it's symmetry breaking. So in infinite volume, symmetry breaking means you're actually not a pure state because you decompose as a convex combination of these other pure states. So this in general is symmetry breaking, right? But these are not symmetric. And so kind of the fusion category symmetry will permute them according to the fusion rules of the module category, exactly as you can see in your categorical Landau paradigm papers where you glue the topological boundary conditions and you have the string operators go across. All of that stuff works at the level of representation theory of C-star algebras. And so as a corollary, you can get this anomaly enforced gaplessness condition, which is that if phi is a pure symmetric state, then it is not topological, pure symmetric state. Then, in other words, because in my world, symmetry breaking means it's not pure. So when I say pure, I mean not symmetry breaking. If phi is a pure symmetric state, then phi is not topological. Or so let me say it this way. Phi is. So, or no, what do I want to say? Sorry. If phi is a topological and pure is topological pure symmetric state, then I'll say it this way: C has a fiber functor, right? Then C is anomaly free. C has a fiber functor. So the converse is what people usually say, because in other words, this thing wouldn't decompose because it's pure, so it's rank, so it has a rank 1 module category, and that's the same thing as a fiber functor, right? So people usually say the converse, right? That if you're anomalous fusion category and you take a pure symmetric state, it has to be gapless. But here gapless just means not topological. I mean, it's not clear to me that the complement of topological is actually gapless, but I think many condensed matter physicists use the word gapless as synonymous with not topological in some sense. But okay, That's why I kind of say it this way instead of saying the gapless version. Okay, but anyway, so this is a familiar result, but you can prove that kind of using these definitions and formalisms at a level kind of lower than just the category picture level. Like you can really get in with the C-star algebra of operators and prove these things. Okay. Anyways, I'll stop there. Thank you.
Hey, thanks a lot. Can I go back to this question that Sal actually raised? So, because you first don't talk about the symmetry boundary, and now, if you just have a physical theory and you construct the physical boundary B, then you could have many different SymTFTs that you could attach to a given physical theory.
So my claim is that actually, no, if you have the whole theory and you have the physical thing as a sub-theory,
Yes.
then that determines what you can glue in there as a TFT.
Okay. So you
Yeah,
kind of do have the full sandwich.
Yeah, you have
It's
the
just
full
you're not really using it. Because, right, you could have many theories coupled to a given SymTFT bulk.
Yep.
And that
Yeah,
doesn't
that's
determine
exactly right.
yet what the symmetry boundary is. Or the
Exactly,
actual symmetry
exactly.
of the theory.
That's right. So if you just have B, you just have the physical boundary and the SymTFT. But once you have B sitting inside the quasi-local algebra A, that algebra is determining the topological boundary, right? So that's
So
this
that comes
question here.
in this condition. Somehow.
Yeah, right here. When you have the A, you need that Lagrangian algebra, and the fact that it's topological is reflected by the fact that it's a Lagrangian algebra that you coupled in. Because right, you could couple in some.
You could,
So
for Ising CFT, right? You could have Z2, or you could have the
yeah,
Ising SymTF, the double of Ising. So it's not uniquely, or put differently, for any Z2 symmetry, there are many theories you could couple that too. It's not uniquely specified. You're
yeah,
saying
that's
somehow
right.
that comes through this additional condition
Yeah.
that B has to sit inside A.
Yeah,
Okay.
B sits inside A, which is totally backwards from how we usually think about it because we start with A usually, and then we take symmetries and we find the B.
That's
But
right.
from a structure theory, I'm saying, okay, if you start from the B, that tells you the SymTFT, and then yeah, it could sit inside a bunch of different A's. But if it's already sitting inside A because you built it from some symmetry, then that A is telling you the topological boundary condition. Yeah, exactly.
Okay. Right, thanks. And when you say mixed states, if I understood this correctly, you don't really mean mixed states, but you mean just SSBs.
So no. So I do. So okay. So in infinite volume, there are many different kinds of non-pure states.
Yeah.
Okay. So there are non-pure states that are just convex sums of other pure states, and that's SSB.
Yes.
But there's also these like violent mixed states, which are like KMS states, which are like thermal type states, right?
So can you also
Those,
study them in this context?
yes, you can. And I've been thinking about that a lot. I've been reading your guys' papers and thinking about how to do that in this context. Yes, you definitely can do that.
And
so
do you
that's
have
what
to use some kind of double picture there as well, or can you just work with some, because you don't really have a, you don't, you don't have a Hilbert space, so maybe you don't need to do that. You just have
in fact,
algebra.
Yeah, exactly. That's right. So in fact, the natural picture does not have the doubled thing in it. And I actually had to work pretty hard to see where the doubled thing comes from, like how to like match it up with like your guys' stuff in the literature. But I think I understand that now. So yeah, you don't have to work with the double thing. And in fact, the double thing only works when it's kind of when it's like a density, like when it's like a thermal state in some sense. By thermal, I mean like the associated von Neumann algebra is not type 1. So it's like a type 2 factor, a type 3 factor, or something like this. So when it looks like like a standard equilibrium state from
yeah, it's a steady state situation.
Yeah, exactly. But in general, like there's a whole general story you can do here, and I'm not exactly sure. Yeah, because I've been looking at your guys' paper, and there was another group at the same time that had a paper, and I'm trying to
there were 3 papers.
Yeah, there were 3 papers, right. So I'm trying to parse all that. So that's something that I kind of have on the back burner now, but it's something I've thought about, and I think it works really nicely. But we should talk about it sometime.
Yeah, it would be actually very nice to extend that to these kind of symmetric mixed phases.
Yeah, that would be cool.
Yeah. Okay, are there other questions for Corey? We had a question already, so if not, then let's thank Corey again, and I'll stop the recording.